Hey, and welcome to Lecture 3 on equilibrium. Today, what we're going to be discussing is the use of ice charts. We're going to use ice charts to calculate K, which is a little bit of a review from our Lecture 2 from last week. We're also going to be using an ice chart to calculate the equilibrium amount of all of the chemicals that are present given a specific equilibrium constant. And then the last type that we're going to use is we're going to be determining how to set up the C row or the change row using the information that we have and creating something called the reaction quotient that we're going to call Q, and we're going to compare Q to our equilibrium constant. So we are going to start today with this first example, and I've got the example already written down. And so what I want you to do is I want you to take a moment, just pause the video so that you can copy this down. And I want you to work this example as we go through it. But I'm not going to give you 5 minutes right now to copy it down. So instead I want you to press pause so that this is still on the screen and just pretend like you're in class. And so you want to write down the information. And then here is the balanced equilibrium reaction. So you want to write it down because that's the first step in solving the equilibrium problem, is write down the reaction. And the second step that you'll do is you'll write the equilibrium constant expression. And then you're going to organize the data. And so go ahead and press pause and give yourself a moment to copy this down. And then once you have copied this down and copied the reaction and written the equilibrium constant expression, then hit play again and we'll continue. But as you do that, be sure that you leave some space here so that you can set up an ice chart, because the focus today is ice chart. So every single one of these is going to have an ice chart. So go ahead and press pause, and I'm going to press pause for just a moment. Okay, so you should have had time to give yourself enough time to write down the information, to write down the balanced equilibrium reaction, and you should have written down what the equilibrium constant expression is. So I'm going to write it on the other board over here. So we're going to do Kp first because we have pressure information that's given to us, and so that would be easier to do the equilibrium constant for the pressure. And so the Kp expression will be your products, which are NO2, so the pressure of NO2, and its coefficient is a 2, so you're going to square that. And then the reactants are NO, so the pressure of NO, and its coefficient is 2, so it's squared, and then times oxygen, so the pressure of oxygen. So this is our math expression that we're going to be using. And remember, keep in mind that whenever you have a math expression, you only have one unknown. And the question is, what is Kp? And so that is going to be our unknown. So we have to have equilibrium quantities of each substance. And so we will be able to figure this problem out once we know the equilibrium amount of NO2, of NO, and oxygen. And so let's go over here to the information that is given to us. And so the given information, it says that a reaction mixture initially contained 1.5 atmospheres of NO and 2.5 atmospheres of NO2. At equilibrium, at 273 Kelvin, there is 0.25 atmospheres of oxygen present. Calculate the K sub P and K sub C. So we're just going to save the K sub C for later because that's a separate thing, Kp to Kc. So if you look, you want to identify a few words here that are keys to knowing this is an ice chart. The first one, it's a reaction mixture initially contained. And so we have an initial amount, and the initial amount is of the chemical NO and the NO2. And then it says at equilibrium, there is 0.25 atmospheres of O2. And so we have an initial amount and we also have an equilibrium amount. And so you want to set up an ice chart And I stands for initial, C is what kind of change occurs, and E is equilibrium. The top row, those are just measurements. And so it's just the measurement of chemicals that there is present at the beginning. And so that word initially gives us an NO. So we have 1.5 and we put that underneath NO. And then we have 2.0, and that's for NO2. Okay, so that gives us our initial. So we've got that quantity's done and this quantity's done. And then at equilibrium, there's 0.25 atmospheres of oxygen. So you go to the oxygen, and the column for oxygen, we don't have anything here, but where the E is, the measurement is 0.25 atmospheres. Okay, and so this is the start of us organizing the chart. So the first thing you do is you have your reaction, and those are your headings, and then you put I for initial, C for change, and E for equilibrium. I and E are measurements. They're not a reaction, they're the measurement. So once you have the given information all written down, then you go back and you start with the initial row. So if you have to have a number in every single one of these columns. So we only had NO and NO2 present. You can't just make up an amount for oxygen. If it doesn't say there was oxygen present initially, then there wasn't. And so if the chemical is not mentioned, then you didn't have it at the beginning. And so for oxygen, we would say we don't have any. And so anything that's not mentioned in the problem as an initial quantity, you don't have it. But at equilibrium, you have some of everything. And so if you look at each column, and now we've recorded all of the information that's given. So now you have to start filling in the information based on changes that occur. And the changes are stoichiometry changes. And so I know I have 1.5 at the beginning for NO, but I don't know anything else. Well, I know I had 0 oxygen because it wasn't mentioned, and it told me at equilibrium I had 0.25. And so the change is always going to be either you create or you destroy the chemical. And so if I had 0, I have to create it, because you can't have anything react if you didn't have any at the beginning. And so wherever you have a 0, it's got to be plus. And so we are going to have to create, and if I went from 0 to 0.25, then I created 0.25. So we created 0.25. And the reason we created it is because the other side had to react. And so if I created 0.25 atmospheres of oxygen, according to the reaction, I have 1 O2 I have 1 O2 for every 2 NO2s. Okay. And so the oxygen will cancel. So for every 2 NO2s, there is 1 O2 that is created. And so 0.25 times 2 would be 0.5. 0.50 atmospheres of NO2. The row that is the change, that is how much amount is either created, that's produced, or how much reacts. And so oxygen has to be created because it didn't have any at the beginning. So if oxygen is created and it's on the other side, this is where the change will happen right here. If it's created on the left side, it must be reacting on the right side, because the only way to create oxygen is for this NO2 to break down. So the change that happens for NO2 is 0.50 atmospheres, and it has to react in order to create what's on the other side. So the opposite side of the arrow, the opposite thing happens because it's a reaction. The NO is on the same side as oxygen. And so if oxygen gets created, then the NO is also going to be created. It has the same coefficient as NO2. So the same change happens. And so we are going to create 0.50 atmospheres of NO. So this change row here, all of the quantities will be a mole-to-mole ratio. 0.5 to 0.25, that's a 2-to-1 ratio. Coefficient, 2-to-1 ratio. 0.5 is created, 0.5 reacts. They're the same quantity because it's a 2-to-2 ratio. Or right here, 0.25 to 0.5, this is a 1-to-2 ratio. The coefficients are 1 and 2. So once I have a number here at the change or a quantity written down, then you're just going to do the math. So 1.5 plus 0.5 would be 2.0 atmospheres. And then over here for NO2, the 2 minus 0.5 would be 1.5 atmospheres. So I have equilibrium amounts for each of the chemicals. I've got 2 atmospheres of NO, 0.25 atmospheres of O2, and 1.5 atmospheres of NO2. Once you have an amount for each of these, you're then going to plug those amounts over into the expression. So I want you to pause the video and take these quantities and plug them into your equilibrium constant expression and see if you can use these equilibrium quantities to calculate the K sub P. And then come back and see if you have set the problem up the same that I did, and then see if you have the same calculated answer. Okay, so what you should have done, you should have written K sub P because that's your unknown. So don't leave that spot blank, write K sub P. And then you're going to plug your equilibrium amounts in the equilibrium constant expression. And so the calculated amount of NO2 using the ice chart, you figured out that there is 1.5 atmospheres of NO2. So you're going to plug in the 1.5 in the place where the pressure of NO2 is. And then you have to be sure to use the superscript. And then for NO, you calculated that its equilibrium pressure was 2.0 atmospheres. And it has an exponent of 2, so you have to be sure that you put down that 2. And then you were given the pressure of oxygen, 0.25. And so we have all of the information organized. They're all equilibrium amounts. And so you're going to take each of those numbers and then you're just going to do the math. So it's 1.5 squared divided by 2 squared divided by 0.25. And I got 2.25. Okay, so just go back and make sure. I got 0.5, 1.5 squared divided by 2 squared divided by 0.25 equals 2.25. So I double checked the calculation again, and I got 2.25 as my K sub P. So that number It's not a real large number, but it is bigger than 1. And so you can kind of evaluate it and see what does it mean in terms of your quantities. And so it is a measure of how complete the reaction is. It's your product versus your reactant. And 2.25 versus 1, that is not a big difference. And so there's not a huge amount of product versus a huge amount of reactant. And so at equilibrium, there's just a little bit more product than there is reactant, or you could say there's about equal quantities of both, because this 2.25 is neither large nor small. It's close to 1. The closer it is to 1, the more equal those concentrations are at equilibrium. So this here is 2.25 is your K sub P. The second part of this question is what is the K sub C? And there was a special equation that I gave you last week to convert between K sub P and K sub C. And so see if you can go back in your notes and write down that equation and look at the data that I gave you and the reaction and see if you can convert between the K sub P and the K sub C. So pause the video, go back and look at your notes, find the equation that I gave you, and see if you can convert between the Kp that you just calculated and the K sub C. Okay, so what you should have found is this equation here. The K sub P, the equilibrium constant for pressure, is equal to the K sub C, the equilibrium constant for molarity, times the product of RT raised to the delta N power. So you have to know the temperature, and you also have to look at the moles of gas that there are for product versus the moles of gas that there are for reactants. And so if we go back to our reaction, the reaction, there are 2 moles of gas as a product, and there's 2 plus 1 moles as a reactant. So our delta N for this, we've got 2 moles of gas minus 3 moles of gas. So our delta N is -1. Okay, and then the temperature that I gave you for this problem is 273 Kelvin. And R is the ideal gas constant, 0.0821. K sub C is your unknown, so that is the thing that you're going to leave as just its letter, K sub C, and you're going to plug the 2.25 in as your K sub P. And so if you plug all those values in, you get 2.25 is equal to K sub C times 0.0821 times 273. Both of those together raised to the -1 power. Go ahead and erase this down here. So we have values for everything except for K sub C. And so you're just going to plug those numbers in, and then you're just going to do the math. Okay, I got 50.4. as my value. And I'm just going to double check and do the math again. So 0.0821 times 273, and then I'm going to raise that to the -1 power. And then I'm going to divide that, which is a really small number. I got this as the answer to that problem. So that's what I got for here. I'm going to divide that number into 2.25. So 2.25 divided by the answer. And I got 50.429925. So 50.4, that's what I got for my K sub C. So if we go back and we look at all the parts of this problem, okay, so you want to copy down the data, but kind of leave it so that you can sort it out later. Don't worry about it. Just get everything down that you know, and then you start organizing it underneath that. And so you want to write down the balanced reaction with all the states of matter, and then you use that to write the expression. So our expression that we were looking at was K sub P because we had pressure information. And so if you wrote out the K sub P, it was the pressure of NO2 squared divided by the pressure of NO squared times oxygen. And it's asking for Kp, so I have to have equilibrium quantities. And so you can only plug in equilibrium quantities. So if you look at the information, you'll see that it's an initial amount. And so initial amounts mean you need an ice chart. And so go ahead and fill in the rows so that they're labeled ICE, and take every piece of information that you're given and place it where it goes. Then once you have that, then you plug in the I column. So every column should have an I piece of information. If you don't have any given, that means that that chemical is not present, so you have to put a 0. So zeros are not understood. You need a number because 0 isn't a number. Wherever you have a 0, the change will always be positive because this is how much reacts or is created. And you cannot react a chemical if you don't have it. And so this has to be positive. It has to be plus because it's being created. But you're told that there's 0.25 created at equilibrium. That means that to go from 0 to 0.25, you had to add 0.25. This number is a mole-to-mole ratio with all of the other ones in the change row. And so this is 1 versus 2. So this number should be a 1 to 2 ratio. This has to be twice as big. 1 to 2. This has to be twice as big. Once you have an initial and a change, you just do the arithmetic going down. So these are two numbers. You just add them. Two numbers, you add them. Two numbers, you subtract them. And then that gives us an equilibrium quantity that we used in the equilibrium constant expression. So this is one using the ice chart where I know how much I have of something at equilibrium, and I know how much I initially had. The next example that we're going to do, we are going to use an ice chart, but there is a different kind of unknown. And so go ahead and pause the video and turn to another piece of paper because you're going to need to have a clean piece of paper in order to do the next problem. And we're going to end up using the quadratic equation. Okay, this next problem, take a moment and pause the screen and so that you can copy it down. So you want to copy down all the information and then do step 1. And so the information is not part of the first step. So you want to copy down all the information that you have. So we have 2.75 molar of phosphorus pentachloride, and it's added to a sealed container at 1300 Kelvin. If the K sub C is 125, what are the equilibrium concentrations of each chemical? So there's 3 chemicals in this reaction. There's the PCl5, and on the opposite side of the equilibrium arrow, there's PCl3 and chlorine gas. Everything's in the gas state. So pause the video, give yourself time to copy this down, and then see if you can start the steps. So remember, just tell yourself, step 1, write down the reaction. Step 2, write down the equilibrium constant expression. And then step 3 is organize the data. And this entire lecture is about ice charts. So you're going to have an ice chart that you have to fill in. So go ahead and start the ice chart and see if you have set it up the same way that I will be setting it up. But give yourself time to see if you can sort this data. Okay, so you should have written down the reaction PCl5 gas, equilibrium with PCl3 gas and chlorine gas. And you should, that was step 1. Step 2 is you write down the equilibrium constant expression. And so the equilibrium constant expression, K sub C, is equal to products over reactant. So PCl3 times chlorine, both raised to the first power. Those are your products. Your reactant is PCl5, and the coefficient for that is 1, so that's also raised to the first power. And so in this problem, when you start to organize your data, you want to go and see if you can find a place for all your data. And none of these equations involve temperature, so you're not going to use the temperature for anything right now. The temperature is there just to let you know the temperature is constant. The temperature has to be constant or you wouldn't have an equilibrium constant. And so in this problem, we have the equilibrium constant 125. It doesn't go in the ice chart. It goes over in the equilibrium constant expression. And so when you're trying to put the information that's given already where it belongs, then you want to go ahead and you want to put the 125 where K sub C goes. So go ahead and put it there, and then you're going to start sorting the data so you can put information on the other side. So K sub C, if you're given K sub C, go ahead and start the process of plugging things into where they go. So that's already there, so I've got that written down. So this one's where it needs to go, so I'm going to cross that one out. The 2.75, it's added to a sealed container, so if nothing's happened to it yet, so it's the initial amount, and it goes underneath PCl5. And that's all I have. I don't know anything else. So there's no other numbers that I can plug in. And so you're going to sort this out just the same as we did the last problem. You're going to start with the initial row. Anything that you were not told that you had, it means you don't have any. And so there's 2 other chemicals. We weren't told that we had any, so we don't have any. So you put zeros there. Okay. That's all. There's no equilibrium quantity, so I can't do any kind of math. But what we can do is we can figure out how much change occurs. This change, they're all some kind of ratio with each other. It's actually a 1-to-1-to-1 ratio. But don't put 1 because you don't know. 1 is a quantity. You don't know how much it is. And if you think back to math, if you don't know something, the most common unknown letter is X. And so if we don't know how much equilibrium we have, then we don't know how much change occurs. And so what we use is we use X to say we don't know how much it is. So X is going to be our change. And the coefficient that goes in front of X is going to be whatever the coefficient is for the chemical. And right now they're all 1s. And so for this change, I've got a 0 there and a 0. Whenever you have a 0, it means that you're adding chemicals, because subtracting means you've reacted. And so on this side, it'll be plus 1x. Because the coefficient is 1, your change is x, you don't know how much it is. You also are creating chlorine, but you don't know how much, so you're going to put plus 1x. And over here on the opposite side of the arrow, if this side is plus, this side has to be minus. So you're going to put minus, and the coefficient is 1, so it'll be minus 1x. So now that we have information in the row where change occurs, then you're just going to do the math to come straight down. And so this would be 2.5, and just don't include the unit. So it'd be 2.75 minus x. So the quantity of PCl5 at equilibrium will be 2.75 minus x. For PCl3, it's 0 plus 1x, which is just x, and 0 plus 1x, which is just x. And so the quantity of PCl3 that we have is x. The quantity of chlorine is x. So I have an x there, an x there, and an x there. And x has the same value no matter where it is. because it's all based on how much reacts or how much is created. Once you know the equilibrium quantities, even if it involves unknown x, you can plug those quantities over into the equilibrium constant expression. So I'm going to move the camera over here. Try to let it focus. Okay, so the quantity for PCl3 is x. So I'm going to plug it in where PCl3 is. The quantity at equilibrium for chlorine is x, so you plug it in there. The quantity for PCl5 is 2.75 minus x. So now I have all the information, every single variable in the equilibrium constant expression has information, and the only unknown variable I have is an x, so I only have one unknown. So now I want you to pause the video and I want you to do the algebra and see if you can rearrange this. If you need an algebra review, there is a math review worksheet that we worked on Friday, so you can go to the team site and you can take a look at the math review that we did on Friday, and you can watch the recorded lecture, or you can just practice the problems in the document that I posted up on the team site. So go ahead and pause this and then come back and see if you have the same math that's set up. Okay, if you're back, then that means that you have done the algebra yourself and you're just double checking. So you want to expand all of this, and then you want to isolate all the variables on one side so that you can solve this problem. And so I'm going to multiply both sides by 2.75 minus x. So 125 times 2.75 minus x. And x times x is x squared. So I'm going to go ahead and multiply that. So 1.25 or 125 times 2.75 equals 343.75 minus 125x equals x squared. Now you have to get all of the variables on one side because you have an x squared and an x and a number term, so you're going to have to use the quadratic equation. So you're going to move everything over, and you want to move it all over to where the x squared is. So I'm going to add 125x to both sides. And I'm going to subtract 343.75 from both sides. So I end up with 0 equals x squared plus 125x minus 343.75. So our A term is 1. There's our B, and it's a positive value. And our C is a negative value. So you're going to plug these into the quadratic equation. So go ahead and use this expression and plug that into the quadratic equation and get your 2x values. And then we have to decide which of our x values is actually something that can exist. So pause the equation, pause the video so that you can do the quadratic equation. Okay, this is the setup that you should have put into the quadratic equation. So your b value is 125, so negative 125 plus or minus the square root of 125 squared minus 4 times 1 times negative 343.75, all divided by 2 times 1. So you're going to go through and do the arithmetic, and you should get 2 values for your x. Only one of those values will be true. So go ahead and go through and get the 2 values, and then come back and unpause to see what those 2 values are. Okay, so this is what I have for the simplified version. And so you got a positive and a negative. So we've got the 130.38, and we're going to add that to negative 125 and then divide by 2, and I get 2.69. That's one possible answer. The other possible answer is when you subtract 130.38. So negative 125 minus 130.384 divided by 2. I got negative 127 or 128. Okay, so those are the two mathematical x answers, but at the point that you get x values, you're going to switch back over into remembering that you're in chemistry. And in chemistry, we don't have two possible answers because this is a chemical reaction. And if we go back to the actual reaction, the x's are quantities. Because it's a quantity, it's a change, it's the quantity that changes. And so we have 2.75 molar of PCl5 that is reacting, and only X amount can react. And so we have two values. The negative amount, or the negative X, doesn't make any sense because if we plug in a negative there, it becomes a positive. And suddenly we are going to be creating 128 molar of PCl5, which we can't do because we don't have any PCl3 to create it. So in the chemistry problems, when you get two values for your X, if you ever get a negative X, the negative will automatically be the wrong answer. So the only possible answer is the 2.69. And if we go back over here, that is the quantity that reacts. And so if I plug in my X value right here of 2.69, I had 2.75. And so I do have 2.69 that can react. And so that will leave me, if you take 2.75 minus 2.69, which is what you're saying is right here, then at equilibrium, I've got 0.06 molar of the PCl5 that's present. I'm creating X quantity of PCl3. So at equilibrium, I have 2.69 molar of the PCl3. And I'm also creating X amount of chlorine. So that's 2.69 molar. So at equilibrium, I've got 2.69 molar chlorine gas. So the question was asking, what are the equilibrium concentrations of each chemical? Once I knew the quantity that is reacting or the quantity that's being created, I can then just add the numbers or subtract them and figure out each amount. You can double check these answers because this is kind of a long process. You can double check these answers by plugging these values back into your equilibrium constant expression. And so if I plug in the values over here in my equilibrium constant expression, this now I'm saying that I think it's 2.69, and this one is 2.69, and this one is 0.06. If I calculate, I should get close to 125. I got 121 when I round it. So the reason, this is 121 versus 125. So the last digit is the one that's off, but that's because this number here all of a sudden just has one significant digit, which you can't do anything about that because of subtracting. And so it's just the significant figures that's off. But otherwise, when you double check it, as long as it equals in all digits except the very last digit, so 120, and that's 100, it'd be 121 versus 125. It's the ones place, which is the last place, that's off, and it's all because of rounding that we ended up having to do throughout the problem. I kept all the digits that I could, but once you start plugging values back in, we got the value because the final answer down here was rounded. Okay, so I have written another example on the board, and this example, we are not going to work this example in this video. What you need to do is you need to pause the video so that you can see this entire example, and this should follow the same format as the last one that I just worked with you. And so again, think in steps. Don't just jump in and start trying to fill stuff out. And so you want to copy the stuff down, and then step one is copy the reaction down, and then you want to, it's an ice chart, so you got to leave space. So you want to leave space, but go ahead and do the K sub P expression so that you have the reaction for your headings, and then you have the K sub P expression so you know what you're looking for. And then you want to start to organize the data. And so you want to look at what you're given and see if you can start filling in the ice chart, and then try to figure out how to complete the ice chart so that you have equilibrium information to plug into the K sub P expression. But I want you to go ahead and try to do as much of this one using the same steps that we did in the last problem. So if you have to go back and re-watch that, go back and see where I talked you through all of the individual steps, make notes to yourself, see how far you can get. You're going to end up using x's, you're going to end up using the quadratic equation, and you're going to get two values for x, and only one of them will be possible. So I want you to do this, and we're going to go over this problem during one of our practice sessions this week. And so you want to have as much of this done, and you want to have questions, but you want to try to use the information that I've already given you in the previous practice problem. So go back and make little notes to yourself, make little step-by-step processes, but this will involve an ice chart. So go ahead and copy this down so that it's ready for you. And then I'm going to move on to the last part of this video. Okay, so we are to our last topic for today, which is going to be probably one of the longest calculation problems that you will do in General Chemistry 2. And we're going to be using something called Q, which is also known as the reaction quotient. I usually say it's kind of a question of where equilibrium is. And so for this last problem, before you start copying it down, I would recommend that you start at the top of a page, and if you usually write really large, you might want to make it so that if you're using your notebook, you might want to make it so that you start at the back of one page, and if you need to continue, then you would still be able to see all your information. And so it might possibly, just depend on how large you write, you might need more than one page. And so go ahead and make it so that you can see all the information. So start at the back of a piece of paper and start by copying down this part of the information, and then write down the reaction. You're going to need an ice chart. All the things today involve having an ice chart. And so go ahead and leave yourself some space, and you want to write down the equilibrium constant expression, and then start filling in the ice chart, and then come back and I will explain what it is that we don't know at this moment for this problem. So go ahead and pause it Give yourself time to organize your data and start step 1, 2, and then 3, which is setting up that ice chart. Okay, so step 1, write down the reaction. Step 2, write down the expression. This is a K sub C expression, because here's your K sub C, and you got a bunch of molarities. So if you look, it says you have 2 molar HCl, 1 molar hydrogen, and 2.5 molar chlorine, and they're present in a sealed container. This is how much there is, and you don't know if it's at equilibrium or not. So let me add this one part, at equilibrium. So this is how much you're initially given, and it doesn't say at equilibrium, so you can't say it's equilibrium. So we're going to write down 2 molar, 1 molar, and 2.5 molar. Okay, we know that K sub C is 4.8. So I'll go ahead and put it down there. Okay, but now we have to fill in this ice chart. And this is going to be a situation, I don't know any equilibrium amounts of anything. I do know the constant. And what we were looking at in the previous problems, there was some chemical we didn't have any of. It was some zero amount. But if you copy down the data as it's given, you'll see that there is a little bit of everything. And so how do I know if I subtract or add? And the answer is not, that's a reactant, you subtract it, because that's not the way equilibrium occurs. Sometimes, because this is both ways, even though we call this the reactant side, the products are also creating the reactants. So you don't know if you have too much product or if you have too much reactant. So we don't really know which way to go. And so it's going to be plus or minus 2x and plus or minus x and plus or minus x. But we don't know which way it is. So this, I don't know. And the reason I don't know it is because the zero of our initial amount was always going to be our indication. Or the first example we did today, we actually had numbers to put down here so I can know if I had to add or subtract to get that number. I don't have any information at all. I have no zero up here, so I don't know which way to go. And so what you do, if you don't know if there's a question as to what side do you subtract and what side do you add, the way that you know that you have a question is because you have an initial amount given for every chemical. You have no zeros. And so off to the side, you're going to set up what's called the reaction quotient. It looks the same as K sub C, but what you're doing is you're taking a ratio of what you have right now. So this quotient is where am I right now? And so what you plug in are not equilibrium amounts, but your given amounts. So in the reaction quotient, what goes in here are your initial quantities. Those initial quantities go there, not the equilibrium, because this is your equilibrium stuff. Only E information can go. But this is, I don't know where I am. And so you're going to plug in those amounts. So I'm going to plug in a 1 for hydrogen, a 2.5 for chlorine, and a 2, and then square it for HCl, because those are your initial amounts. And then you're going to do the arithmetic. So 2.5 divided by 2 squared equals Q, I got 0.625. Okay, so I'm going to turn the board around so that we can just talk about Q and K. Okay, so Q versus K. So Q is the initial or given quantities. It's based on that ratio. K are only based on equilibrium quantities. And the way that you can go from the initial amounts to the actual amounts that you need is by subtracting a little bit from one side and adding a little bit to the other. And so the reason that we're going to use this is so that we can know which side do you add and which side do you subtract. So which one is it? So you're going to compare Q versus K. So we have for our Q 0.625 versus our K, which was 4.8. So let me see if I can get this zoomed and focused in. It's not focusing. Okay, so the Q is the number that needs to change. The K is what it is. And so you want to ask yourself, is Q too small or is it too large? If it's the same, then it's at equilibrium. And so our Q, this is too small. I need it to be bigger. And so if we just take a look at our information, the ratio, it's your products, which are hydrogen times chlorine versus HCl squared. Okay? If it's too small, that means that the ratio is too small and I need it to be bigger. So I need it bigger. I need an increase. And since this number is based on a ratio, the only way to make it increase is to make your numerator increase. And so the reason it's too small is because I don't have enough product and I have too much reactant. So I need more of the product and I need less of my reactant. So need more, I'm trying to figure out, do I plus, do I add, or do I subtract? If I need more, then on the product side, I'm going to be adding. So it's going to be plus X. On the product, on the reactant side, I've got too much, I need less of it. So I'm going to subtract on the reactant side because I need this value to become larger. Now, the opposite would be true if the Q is too big. So you don't want to look at K and say, is K too small or too big? Because you can't change it. This is the value that needs to change. So I'm going to go back across the board here. Okay, so my Q value, these values were too little. They were too small. So I was trying to figure out, do I add or subtract? So we already figured out that they're too small, so that means I need to add. So my quotient allowed me to answer the question, what side do I add and subtract? So both of those needs to be add. On the opposite side of the arrow, the opposite thing happens. And so my reactant, I now know that it needs to be smaller, so it's going to be minus. It's 2x because my coefficient is 2. So my ratio is x to x to x. It's going to be twice as big because it's a 2 versus a 1, a 2 versus a 1. So I'm going to erase the Q information. And then you just bring your values down. So it's 2 minus 2x will be our quantity for HCl. And it's 1 plus x for hydrogen and 2.5 plus x for chlorine. And so you're going to plug in each of these. The entire expression goes into its location. And so for hydrogen, it's 1 plus x. And for chlorine, it's 2.5 plus x. And for HCl, it's 2 minus 2x squared. And so at this point, you're going to just do the algebra. So I'm going to leave it right there, and I want you to go through and complete the algebra portion. This is going to be a little bit larger because you've got a polynomial that you got to create on the top and on the bottom, but I want you to go step by step. I want you to multiply out the top, multiply out the bottom, and then you have to move the bottom over, but don't try to do everything all at once. But give yourself space so that you can do all of the algebra. And we're going to start the practice sessions this week by going over the last example to answer questions, and then we'll talk about the math for this one to make sure that you've done the math correctly. And we'll do a few more practice problems involving equilibrium during our practice session this week.